So to find the derivative, we first need to identify which rules are in play. You will see that we have an outside function, cotangent, and an inside function, sine t over t. So by the chain rule, we'll need the derivative of the inside separately, and when we take the derivative of the inside, we'll need the quotient rule, which is low d high minus high d low all over low squared. If you haven't seen this notation before, just another way to write the derivative, it could be prime, or just like d high, the derivative of the high function. So we'd write z prime. By the chain rule, first the derivative of the outside, just like unwrapping a present, you have to get the layers out from the outside first. Derivative of cotangent is negative cosecant squared. Then the inside stays the same, don't mess with that inside. And by the chain rule, we take the derivative of the inside. Now that also needs to be the quotient rule. So we have low d high minus high d low. Low is t. The derivative of sine is cosine minus the high function sine times the derivative of low, which is 1, all divided by the low function squared. Now we've differentiated every piece of this. All we need to do is clean it up. There's not a lot we can do. Maybe we move the green part forward. T times the cosine of t minus the sine of t all over t squared times negative, we can put out there if you like, cosecant squared of sine t over t. Now there might be some of you who are inclined to distribute the negative over this fraction. That's fine. We also can share the denominator. So we have these three terms. This is effectively the same thing as writing 1 over t squared. You can make that negative if you want. So I used this negative sign here instead of up here with the distribution. And then we can multiply by t cosine t minus sine t, and then multiply by cosecant squared sine t over t. Perhaps that's a little bit better. Now we have still two denominators. Sometimes there's just not a lot of simplification we can do, but we have the derivative of z by the chain rule and the quotient rule together. These problems are some of the bigger ones, the big deal problems that have a lot of inside. So we apply the chain rule a lot of times with this problem. Let's identify the layers that are involved. The first thing we could cover up is the inside, right? So we have one outside layer, biggest one, that's blue. All this stuff to the third power. Then we go to the inside of that, we have e to differentiate, e to the sine of some stuff, and that's the next inside, the sine. And then inside the sine is yet another function, t over 2. So we have a whole bunch of parts here. Let's differentiate them according to their color. Y prime, outside in, just like opening the present, peeling an onion. 3 times the leave the inside alone to the second power. That inside does not change, not even one little bit. E to the sine of t over 2. Then next we look inside there, see what we can cover up with our finger. What we can cover up is that sine business, so we take the derivative of e, which is still e to the that stuff. Leave that stuff alone, sine of t over 2. Now we look at that, the blue has been differentiated, the green has been differentiated. We need to look inside at the black and take the derivative of the sine of t over 2. If we cover up the t over 2, that's the inside, so let's differentiate sine. The derivative of sine is cosine. Leave the inside alone, t over 2. And then finally we can look inside the cosine and take the derivative of t over 2, which is 1/2. remarkable, but we did the derivative, right? We took the derivative of every color and we did it on their own accord, and we did not mess with the inside of any function. So clean this up a little bit. 3 over 2, those are just constants, times the cosine of t over 2 times e to the sine of t over 2 times e to the sine of t over 2 all squared. Now if you remember properties of exponents, a power of a power means we can multiply. So we can multiply these two powers of e, which is 3/2 cosine of t over 2 times e to the sine of t over 2 times another e to the 2 sine of t over 2. 2 times sine is 2 sine. And then we have the same base and different exponents. So in theory we could just add these exponents together and get 3/2 cosine of t over 2 times e to the 3 sine t over 2. And you have 2 of them plus 1 more. So there's e to the 3 sine t over 2 for y prime. So let's look at one more. This one is huge. We have cosine to the 4th and secant squared. So it will help us to write this again. Instead of cosine to the 4th, let's write it what it really is. Cosine times the secant of 3t. Secant of 3t gets squared, and then the cosine gets raised to the 4th. So look at all of those layers. I don't even know if I have enough colors for this. Outside layer first is 4, so that's pretty nice. Y prime is 4 times all that stuff, leave it alone, to the 3rd. That's power rule. And the inside is the cosine of the secant of 3t, that's squared. So when we look inside this stuff, so we're looking just at the black function, we want to differentiate that. The outside of the black function now is cosine. So we can take the derivative of cosine. The derivative of cosine is negative sine. Leave the inside alone. That's the secant of 3t squared. Then we'll look to the inside of the sine. What are we taking the sine of? We're taking the sine of secant of 3t squared. So there's another outside, and that's the square exponent. So we can take the derivative of that, power rule, 2 times leave the inside alone to the 1, and the inside is the secant of 3t. So we'll look inside now at the black stuff. What's the outermost layer of the black things? And those are secant. Now we have to multiply by the secant. I'm out of space to the right, so I'm going to write it down here. The derivative of secant is secant tangent. Leave the inside alone, still 3t. And lastly, we can look to the interior, to the black function. It's the same function, just shows up twice because the derivative had 2 arguments. Still, there's only one true thing that we need to differentiate, and that's this 3t. And the derivative of 3t is 3. So we did it. We used every color that there is, and we differentiated all the black stuff, and we got each of the layers from the outside in. Maybe we can clean it up a little bit, so check out the constant values. We have a 4, a 2, a 3, and a negative. So 4 times 2 is 8, times 3 is 24, so that's negative 24. Here's a secant of 3t and another secant of 3t, so that's like a secant squared. So let's write the tangent first. He has the lowest exponent, tangent of 3t times secant squared of 3t. Then we have a sine of secant of 3t squared and a cosine of the secant of 3t squared to the third. My. If we were to write this again, how we do with our lazy trig exponents, 3 tangent of 3t, secant squared of 3t, sine of secant squared 3t, times the cosine to the third of secant squared of 3t. So that's a little less intimidating. Part of the reason why we let the trig exponents get inside one less set of parentheses, which can become a pretty big deal when you have a lot of them. But if you can do that derivative all by yourself without any help, you are an expert at the chain rule. So I encourage you to practice. There's more in the lecture notes and plenty in the homework. Let me know if you have questions.